theoretical approach and how to understand that the desalination process based on the mathematics. That means headache, right? I make you headache a lot today. My background is chemical engineers, and also I got a degree in California, University of California, Irvine, for the water engineering, and specifically, I'm a applied mathematician. So most of the mathematics related to the process engineering and statistics. So that's my major. And so my students, I'm sorry, my students who want to join my group, they have to do a lot of mathematical work and also computer coding and optimization study. So today we will focus on how to optimize to run the desalination plants and process based on the mathematics. So you will enjoy the mathematics today. So I'm going to introduce about what is that modeling and what is the definition of modeling and membrane-based processes, and also the consideration of what's the point to optimize the processes. What is model? An example. What is model?
Simulation.
Huh? Simulation. What is model? Procedure.
Yeah.
Procedure. You guys so academics. Huh? You guys so academic. This is model, you know. This is model. So then, what do you think? What do you think? Beautiful, right? Handsome, right? And the others, what do you think?
Same you. Same to you.
Same to me. Thank you. Yeah. You're a very good student. Okay. Yeah, this is me, right? So I'm gonna give you the quick lecture for what is modeling. So everybody has the modeling scheme in your head. Within 0.3 seconds, you will set up the model and compare the model with your thinking. That is, we call that kinematic cycle. Kinematic cycle. That is, you can find your dictionary. That is a very philosophical approach if you cannot understand the language. This is, so we can say this is the theoretical word, model. Theoretical word, model. This is target system. Target system is a real word. So I can say that this is model. This is you. Real word is you. This is model. Can you understand that? Okay. So when you used to see this model walking in the floor, and you will bring up that idea that, oh, this model has a very good fit, a very good clothing, very good fashion, right? That's a simulation. That's a simulation. You will see the model and bring up that idea. Oh, very nice, good, fashionable, something like that. That is simulation. And then you may see yourself. This is real world. Oh, that's not see that. Oh, observation is a see, monitoring. After seeing your real world, oh, this is not fit for me. Oh, that guy is super pretty than me, prettier than me. That's observation. That's observation, right? And then you go to the model again. Another model walking and walk the model like me, and they enjoy. Okay, that guy is a model. Our real world is very close together. We are very close together. We are doing this cycle. When it can stop? When it can stop?
When you meet your target.
This model meet this target. That is modeling. ING is ongoing process. That's modeling. So model is real, not real world. That's a theoretical, our dream. But modeling is our action to meet this model to target. So you may see that model walking from the floor, and then every change of the fashion, then eventually you will find, oh, that's my style. Then you can stop, right? That can happen within 0.3 seconds. That's exactly same time when a boy meet a girl falling in love. That's 0.3 seconds. Yeah, exactly same time period, 0.3 seconds. We call that as numerical circle, this one. So you should do that, iterate again and again and again when this model can meet this target system. When you set up this model, then we can divide as 3 different topics of this method. Modeling for deterministic model. There's mass balance, energy balance, and momentum balance. That is mass conservation, momentum conservation, and energy conservation model. Second one is stochastic regression and probability, and another statistical model. The last one is empirical model. There are, so far, there's no equation for explaining this phenomena. Then we can set up the empirical model. Would you bring that textbook to me? Yeah. Yeah, that's my books. This is the reason I'm here, to sell. To sell the books. Okay. Yeah.
That's the statistics part.
That's one of the model. Belongs to this stochastic model, and that's my book. And if you're interested in there, I can buy that. No, I may give you. I don't know how many that textbook I have, and I can give you with my signature. Maybe they have 2 now. I will check it. Okay. So modeling is starting from this model and target system comparison. That's modeling, ongoing process. So why we call the sampling? You can see the back side of this textbook. Yeah, back cover. Okay, back cover. Then you may see here, back cover. There is another language, sampling, right? Sampling. Why we call that ing, ongoing, that format? We call sample. We can call model. But why we are doing that ing, the ongoing format? Sampling, modeling. Why?
Because it's a continuous process.
Yeah, that should be. Do that again and again and again. It's ongoing process. Cannot stop. Cannot be 100% right. So we have a population, right? We have population. How many samples you have to take? Do you know? We don't know. Yes. Let's say that we collect that temperature here. Where this temperature location? Where? Tell me. Where should that temperature location? Here? 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 Yeah, that's the reason we need a sampling. We have to do that random sample to get that objective result, right? That is science. That is science. Statistics is a grammar of science. Grammar of science. And modeling is a grammar of engineering. So statistics is grammar of science. Modeling is a grammar of engineering. So starting with this modeling, and we can do this control approach, how to do this optimization, how to save that money, cost analysis, and what is the solution for expert system or decision-making system. First one is modeling. Today I can give you this example of CFD. Anybody knows that? CFD, civil, chemical, CFD, computational fluid dynamics, CFD, computational fluid dynamics, and image and numerical analysis. I will give you the example, and the process model and how to control. That is reverse osmosis, forward osmosis, pressure retarded osmosis, membrane distillation. So, did you guys learn this one? Professor Kim? Just the RO, not this one. Forward osmosis. Somebody teach you? No, not yet. Today, that is somebody. This is somebody. Pressure retarded osmosis. No. Okay. I will give you that. So we will learn about control, real-time control with Kalman filter. Kalman filter is one of the engineering tool to remove that unnecessary signals. Then dynamic control for reverse osmosis and cost analysis and optimization that might be happen using this artificial neural network, AI, artificial intelligence approach. And the last one is after controlling, modeling, optimization, and we should say something as a decision maker. So decision maker need this expert system and decision support system. So this is a desalination system design and model development, pilot system, data collection, model integration with validation and verification style, and expert system can support your decision making. Reverse osmosis you have learned, right? You have seen this one. So intake, pre-treatment, reverse osmosis, main process, and post-treatment. Usually we have a two pass. First pass remove that almost 97% of the salt, and second pass 99.9% of salt can be removed. And then storage, we have to do the remineralization for drinking water, and this whole process needs some acid, chlorine, and anti-scalant, sodium bisulfate, and any other chemical cleaning procedure for removing some pollutant for drinking. That is a typical reverse osmosis system. We have advantages and disadvantages. Advantage is very low energy consumption comparing to the distillation, that boiling system. It takes almost 10 kilowatt hour per cubic meter, but reverse osmosis is 3 to 4 kilowatt hour per cubic meter of water. And the high quality of fresh water, so one of the indexes is the sodium removal ratio is under 100 ppm. 100 ppm. Disadvantage, as you know well, there's fouling. The membrane cleaning and replacement, and then this cleaning and replacement needs some cost. And the pre-treatment, we need almost like a similar system for drinking water system, MF, UF, DMF, DAF, that is all membrane system. And anti-scalant, that's chemical, we have to add to remove that scalant. And eventually it needs cost increase. So seawater reverse osmosis is a membrane filtration, and the types of membranes might be polyamide, PA membrane recently, and membrane module configuration, usually most of that is a spiral wound type. Have you ever seen?
Yes.
Downstairs, right? But you did not understand. 기박사? 기박사한테 우리 실험실에 있는 멤브레인 옆으로 잘라놓은 거. 저쪽에 있을 거야, 저쪽. 멤브레인 이렇게 옆으로 잘라놓은 거 좀 가져와 달라고. 기박사 불러주세요. 네, 저 이쪽으로 와달라 그러세요? Any other questions so far? So, I think I will show you that. See, this is introduction. From now on, it contains a lot of equation. It starts. This is a model. We have model. You want to learn? Solution diffusion model. It's a chemical potential, activity coefficient, effective concentration. Is 1, 2, 3, 4, 5, 6, 7 to 10. Then it's A and B. You want to learn? I will give you a quick analysis, but we'd better drop by my laboratory to see the small system for each. That's better. If you want, then I can teach you today. It makes you all confused, and you can enjoy the universe, chaos. So, reverse osmosis. Reverse osmosis needs here high pressure pump, right? Yeah. To squeeze the old salt to make it drinking water. But forward osmosis has a opposite direction. It uses natural driven pressure. We call that osmotic pressure. Osmotic pressure. Do you know that? Do you like kimchi? Enjoy it? Today you may, if you see the kimchi, then you have to bring up this science. Wow, forward osmosis. Yes. We have a cabbage, right? If you put that cabbage as a raw state and then spread salt, right? And waste some time. This size of cabbage shrink down to the small size of cabbage. Why? If you spread the salt located the skin of cabbage, it makes an osmotic pressure. So inside of cabbage contains water. right? This water penetrate to this cabbage skin to the salt side. That's the reason this size of big cabbage shrink down to the small size, and around that environment, you may see water. This water with salt. If you want, we can do that now. Yeah. Yeah. That's the life science, a very simple life science. You can see that, wow, put that something like cabbage, which has a very sensitive skin called the membrane. It has membrane that try to use this for osmosis phenomena. So here, this is a feed, and this is a draw. Draw solution means a salt. So you can put this salt here, then this cabbage side, it has water, try to move there. That is an osmotic phenomena, osmosis, we call that, osmosis. Natural driven here. That's naturally driven process by osmosis. And theoretically, no energy is required. You know the root of any plants, how they can suck in the water from the soil. Osmosis. I gave you the answer today. This is osmosis. This is reverse osmosis. I'm giving you this pressure retarded osmosis here. How can the root of any plant suck that the water from the soil? That's osmosis. The reason is, which part is more that salt, not salt, water, humid, and some vapors. Soil contains water or water vapor inside, right? But inside this plants, it has some nutrient inside it. That means high concentration. Inside of a root, high concentration. But outside of the root in soil, low concentration because it has water. So that low concentration water penetrate that root skin, and eventually they can suck in the water. And next one is a capillary phenomena. Capillary phenomena. The last one is evaporation from leaf. There's three combination of phenomena. These three phenomena is combined to survive the plants. Three: evaporation, capillary, and osmosis. The starting point is osmosis. Okay. But unfortunately, this forward osmosis should install another second process. That means recovery system, separation system. We have to separate this draw with water. Draw with water should be separated, and then this draw solution can be recovered, and finally this final product can be separated. So in thermodynamic first law, there's no free energy. There's no free energy. That means reverse osmosis needs high pressure, right? High pressure. But forward osmosis needs separation process. That is another energy we have to consider. This membrane system as it is, it's natural, no energy theoretically. But separation system, we need energy. So that's the reason there is not popularly used, this forward osmosis. But this is popularly used in military, army. So there is a sugar pack. There's a sugar pack. We have two envelopes. First envelope here, second envelope here. in between we have a membrane here. I have that one in my lab. But this pack separated by membrane. But this pack contains a high concentration of sugar. And this is empty. This side is empty. So whenever you go, any river, any dirty water, you can put it into here, this side. Dirty water is okay. Any polluted water is okay. Sometimes if you are emergent system situation, you can use your urine here. You can use your urine here. Yeah. Temperature is a little bit warm, right? A little bit, but it's drinkable. It's drinkable. So that this membrane start to separate the water, only water, to sugarose size. And then you can drink the sugar water. That is a military army for the osmosis system. There's no energy. If you are very urgent, then you can press this envelope. So that's a forward osmosis commercialized use. So I try to use my urine. So that disadvantage is temperature. I like ice. I like ice water, ice coffee. But urine temperature coffee is my body temperature. So I have to drink that a little bit warm water. That's sugar water, not urine. 100% rejected. But this draw is a sugar side. The pure water is separated out of this diluted draw solution. Draw solution is recovered to be sent back to the membrane process here. So we can utilize that one.
So the draw solution is not only for salt,
No.
it also be used for other.
Usually we use that carbohydrate. Not in the lime. Yeah, that's in lime, right. But that is usually in ammonium bicarbonate. Ammonium bicarbonate. So CaCO, some CO3, something like that. That is used in your baking powder. Yes, baking powder. Yeah, baking powder. But it's edible, right? It is edible, but I don't recommend to drink. Right? But that is used for your baking powder, right? But this is a cheap one. So this is the normal, this ammonium bicarbonate is normal draw solute, and you can utilize their concentration adjustment here. And this is the theory. You have to understand what is osmosis. Firstly, we have to understand this chemical potential. There's no language like chemical potential. I will tell you the chemical potential. Where did you get that coffee? That one? That one? How many days you have more? No, for this training. This is last day. Wow. Then I can tell you. There's another coffee machine there. You can. Did you use it?
No.
Why not? Oh, I didn't. He is my TA, and he is my my research professor for this lab. He's my TA. Yeah, explain this structure to them. 그 11시 반에
예, 지금
아,
말을
그러니까.
해놨습니다.
세 군데 혹시 오퍼레이션 할 수 있으면 하고 안 되면 그것도 보여주고 오케이 하고 그다음에 그리고 괜찮아. 그리고 뭐 저기 PRO도 성우 혹시 있으면 설명해 보라 그러고 되면 돌아올려 보고 멤브레인 있으면 보여주고 멤브레인 같은 거. 있는 거 다 보여줘도 돼. 포워드 오스모시스도 포워드도 있잖아. 디스크판으로 있는 거. You have learned, right? Do you know this? Yes? Come here. Explain it. You said that yes. Okay. Reverse osmosis, water from here, right? Here. But you can see there's some layer here. Can you, somebody ask, tell me, or tell you, right? Somebody explained this one already? This is a seawater.
Show us the picture, but not really.
Okay, seawater goes to here, and in between there is some layer, some chasm here that is we can push the water. Then that goes to that empty layer, accept the water inside here, and then why this is a road?
For bigger surface area.
Yeah, for bigger surface area, right? But how to squeeze out the water?
Pressure.
Huh?
With the pressure.
Yeah, high pressure. Then water rotated inside, like your toilet paper. Toilet paper, push that this side, and then roll in, and there is some hole here, right? Hole here. There's a squeeze out all the waters into here. And so hydrodynamic inside of this membrane roll in here, or that the surface roll in here, water try to follow this waterway of road, and then eventually this hole collect the fresh water. Sometimes we call this as leaf. So it makes that, how to say it, two leaf. Here, one hole and two holes. We have two holes. Then, starting with this two leaf, it's wide range of two leaf from this center hole, and then rolling. Can you understand that? You can see here. This is first leaf, this is the second leaf, and then roll it. See it? Nobody explained it, the detail. See? Two leaf, roll it. In that way.
But what is this one that is thicker here?
Yeah, this
But
is
one
leaf.
spacer, the small one.
Yeah.
But what is the one that is more thicker here?
This one is first,
Also spacer?
that's a spacer.
Oh, it's thicker there. Why?
Mhm. Because if you put these two leaves, it's not stable
Okay.
for the first area, first skin. But from the second skin, it has a waterway. The first skin cannot make the waterway. That's the reason it makes that. Some stitch there. So we call this two-leaf membrane.
It's continuous inside. The hole is continuous inside.
So this membrane has these two holes, two leaves,
Yeah.
starting with this format here, and then roll it. That's the way, roll it. Then it has a two-way of direction, right? One leaf is here, the other leaf is here. You can see them. And then we have a two membrane here. Here. That is waterway, this space, right? Inside this space. So if you unfold it, toss that one. If you unfold them, looks like that. Unfold that looks like this. And where is the direction of seawater? Here. Right? Right? That's road, right? But if it had unfolded, looks like this two-leaf system. There's a four-leaf also. It depends on the company. Four-leaf. So two-leaf, four-leaf, and roll it. You can understand, right? Then, this way, this is roll it. This is seawater. And then, this is membrane, right? And this, inside this space is a hole. This space is a waterway. So this seawater squeezed, high pressure, and then by following this waterway and this hole, accept that fresh water. That hole. Can you understand that? Okay? Graphically, you have to understand that is reverse osmosis membrane. So we call this system cross-flow system. Cross-flow system. Why this is cross-flow? Enters in this way, goes that way. This is cross-flow. That is cross-flow. So reverse osmosis in a spiral wound system looks like that. It's a cross-flow. A cross-flow usually shows that high performance. Fluid dynamics said that. Fluid dynamically, it shows a high performance. So, understood, right? If you see that one, understand, right? You don't understand?
I think when the membrane weight increase the moment forward the arm not come in.
Yeah, starting from here, and then this is rolled. Not from the outside. It starts from the inside here. This. So, before we roll it, this shows this two leaf. We call it two leaf. This leaf starts to roll from inside. Then looks like that. That is 8-inch. And when they roll it in 8-inch, then stop. So water goes to that way. See that? So if you unfold it, unroll it, then goes there. That is this direction. Here. This direction. And then goes out. Actually goes in. Goes in. This is drinking water system. But for the osmosis, we don't need high pressure. We don't need high pressure. Yeah, you can put it on here. And also, if you see, you can. Did you see the spacer here? Spacer inside? Did you see it?
I see in the other.
Yeah, here. You can feel it. this is a spacer. Here. That. Why do we need a spacer? Why do we need a spacer? Yeah, you can.
Space for the water.
Space for the water. Nope. Here.
So,
Top one.
For filtration?
This one.
No. Otherwise it will stick.
Why do we need a spacer? Okay. I hope that you can enjoy this one. It's a simple design. All the ideas start from here. And how to lower it, that's the technique. It's a very simple design. Right, that one. It's a very simple design. And why do we need a spacer?
This is the polysulfone to support the polyamide, the surface. So we need the polysulfone layer. This is the spacer. No.
There is one membrane. There's one membrane. Skin layer, support layer is one membrane. So let's say this is membrane. This is a support layer. This is one membrane. We have a two layer, skin layer, support layer. When seawater goes to here, let's say the high pressure, then it makes like this boundary layer thickness. When you have a membrane, then this has a boundary layer thickness called a concentration polarization. Concentration polarization, that means it inhibits to penetrate this way, water flow. It inhibits this one. This is, we will learn a little bit later. This might be that concentration polarization, boundary layer thickness. This hinder to penetrate this water to the other side, right? Yeah, this is phenomena, mass transfer phenomena. So if you put that spacer here, you can feel it inside. Some spacer looks like that. Try to find it. No. Be brave. It's okay. It's already broken. Be brave. You can feel it. Right? And this is a spacer here. The reason is this spacer's role is, let's say water goes to in that way. See here. Water goes in that way. This is a spacer, right? This is a spacer. Water goes in that way. Then, see, this concentration polarization is broken. How to do that? Meet this spacer broken. Meet this spacer broken. Meet this spacer broken. Broken. So this concentration polarization was broken down to that way. So this layer, originally if we don't have any spacer in between, this concentration polarization boundary layer thickness inhibit and hinder to water penetration, this one. But if you have that spacer makes that broken this boundary layer go and meet and broken, meet, broken, 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 broken. Then this is the theoretical approach how to make that water can penetrate in thin layer. This thin layer, to roll it, we need that spacer. Not only for reverse osmosis, but also for forward osmosis, pressure retarded osmosis, membrane distillation, to make it spiral wound type. That should consider this concentration polarization. That is concentration polarization. So you can answer that. Why do we need a spacer? And you can answer to reduce down concentration polarization. Okay. So osmosis need solvent and solute. Solvent and solute. And also osmosis phenomena is a potential theory. Chemical potential. So when you have a coffee with water, let's prepare this to separate it. Let's do that. Why not? I'm sorry, I touched yours. So, let's say this is water here. Water here. We call that chemical potential, water chemical potential, coffee chemical potential. Let's say that, okay? Water chemical potential, coffee chemical potential. Which one has high potential for water chemical potential? Water. Because it's a water chemical potential. Water. Coffee chemical potential. Which one is high chemical potential for coffee? This one, coffee, right? But if we mix it, this is a high concentration, right? This is low concentration, right? But which one is a high water chemical potential? Right? This is high water chemical potential, low water chemical potential, because we don't have water here, right? That you mean that energy should flow high to low, right? High to low. Which water chemical potential is high? Water. This is low water chemical potential. So it moves. When they can stop? Equilibrium. We call it equilibrium of what? Equilibrium of water chemical potential, right? Then stop it, right? That is osmosis here. Water chemical potential, draw low water chemical potential, right? Right? Coffee, water. Then why? Let's say this is can be mixed in this state? No. When they can mix, if I push that, put it into here, right? But without my action, they cannot mix, cannot be mixed. That's the reason we call that potential. Potential. Potential is not energy. This is a kinetic potential, and position is high. They're whining me. Whining with it. This is locational high potential, right? Potential. we call that potential energy, right? If I drop it, then energy. When they can transfer that energy to on ground. Before meet this ground, this is potential. Potential. Same idea. Without mixing, they have potential. Potential. But how they can mix? Then my action, this as it is can be mixed, right? Why they can be mixed? In this state, this potential switch to energy. We call that mixing energy. In this state, we call that mixing energy. But before mixing, we call that potential. Okay? That's the reason we call this forward osmosis has a mu is a chemical potential of water. Mu is chemical potential of water. Feed higher chemical potential of water. Draw lower potential chemical potential of water, right? So high energy is supposed to move to low energy, right? Between, we call that semi-permeable membrane. Semi-permeable is a selectivity for water. Selectivity for water. Then this high chemical potential of water, energy is moved. That is natural energy. That's a natural energy. Like this mixing. Like this mixing. This is mixing energy is also natural energy. So naturally driven process without any hydraulic process. This is gift for you. This rotational energy is additional mechanical energy. This is not potential. This is actual energy with chemical potential and my mechanical energy. So you have to pay me then. So this is no energy we need. Another one is the pressure retarded osmosis. The more interesting. Forward osmosis can generate water, right? With natural energy. Osmosis. Pressure retarded osmosis generate energy, not water. Generate energy, not water. I'm the consultant. I used to be consultant of this Statkraft. So this is fresh water. This is seawater. Which one is high water chemical potential? Fresh water. You can say coffee. This is just water. Fresh water is just fresh water. This is a salty water. You can say there's some coffee, concentrated. So water chemical potential is fresh water is high. That's obvious. So river water or any area like an outlet between ocean side and river side, we call it confluent of river and ocean. See, coastal area, many country, most of your country has this confluence, right? This confluence size, you can put this generating plant. This is just imaginary view, but now it's working in Norway, Korea, Vancouver, Canada. We try to construct this generation plant, PRO, pressure retarded osmosis plant. Fresh water goes there. Here is a membrane, big membrane. It looks like this, but this is conceptual viewpoint. Water this high water chemical potential is supposed to move there, right? Seawater. This membrane makes that forward osmosis kinematics here. And then water are supposed to go there. But this box constraint is very rigid body. It's not moving. And then when the water goes to that rigid body, seawater container, then inside of pressure is increased, right? Water is moving to there, but this container is rigid. It's not moving. But eventually it will be exploded, right? Just before exploded, make a hole, one hole here. Then it shoot the turbine. It shoot that turbine, then rotate it. That's energy. We call that osmosis energy. Pressure retarded. We have to retarding here. Retarded. And then osmosis shoot that pinpoint, make a pinpoint and shoot it, this turbine blade, it makes the energy. You will see in my lab there is pressure retarded osmosis. So high pressure pump, no, there's no high pressure pump. Only we need is a river water, sea water makes that membrane in between, and then makes the rigid body here. Container should be capture that water and then push one pinpoint of hole, then it shoot to the turbine blade and rotate it. That is energy.
And what's the pressure exchanger used for? The pressure exchanger, what is it used for?
This one?
Yeah.
I will explain that. Yeah.
So what is the ratio of the volume and the energy produced?
That's a research part. My student is working on that. Okay. Yeah, it doesn't matter. It's if you make it this type of membrane, size doesn't matter. But you mean that efficiency of energy. Oops, I'm sorry.
There is a significant amount of
Yes. Now it's commercialized. This pressure exchanger, first one is to extract or to induce the water, import the water into this side. We need a pump here, right? Also to introduce this water, seawater to this container, we need a pump here, right? So this pump energy can be recovered by pressure exchanger. Some part of water goes there, then rotate the turbine blade. Then the other water goes there, and inside here pressure is exchanged. So the pressure exchanger eventually make that no energy need. Pressure exchanger. So we need the initial that introducing pumping energy we need. And the 1 turn or 10 turns of this system, and then the pressure exchange start to work, then we don't need another energy to run it. This is a pressure retarded osmosis, and my lab has a must be the top leading research group of pressure retarded osmosis in the world. So most of the research related to PRO is my student, and my group is the best research group in the world. And also I introduced this one into Korea. And Korean government started 5 years ago. We started almost a $30 million project to develop a small scale of this pressure retarded osmosis. Now it's working. What time is it? Tell me
11.
Tell me 11:30. We will visit my office. This is pressure retarded osmosis. See here, low saline water, seawater, energy recovery device. Then you ask me that here, this one. So this needs some pumping energy, and then initially input this energy and membrane. This is pumping energy here, because we need seawater. Introduce this high saline water, and this membrane naturally driven process. This is forward osmosis process, and then this goes to the volumetric increase. This volume increase, rotate this turbine, and then brackish water. It has 3 advantages. So that's the reason I put my effort on this PRO research. First one is, if you use this reverse osmosis, what is the problem? What is the problem? Brine. Brine, concentrated. See, seawater can drink, but the other one can be concentrated. That is another wastewater, because double times of salt concentration, because we removed, right? We removed for drinking water. Then the other part might be concentrated, right? That is wastewater. That should be treated. There is another treatment we need. Also, we discharge that one into the sea. Another pollution, right? For the osmosis disadvantage, we need this separation technique. But pressure retarded osmosis, first one, seawater can be used, right? And then river water can be used. River and seawater can be used and generates energy. And then they meet together, this brackish water. Seawater can be reduced down. We will learn with reverse osmosis system. So this low saline water, brackish water, we don't have any environmental impact. But reverse osmosis has an environmental impact. Brine, concentrated water, right? So that's, it has 3 big advantages. We will touch that one after combining all the processes. Clean energy, CO2 free. That means we can suggest that for the Paris climate agreement. This is free energy, new renewable energy. Last one before we move, the membrane distillation. In this process, reverse osmosis, forward osmosis, pressure retarded osmosis, all osmosis. But this process is a distillation, but with membrane. Distillation with membrane. But MSF, that is, this just distillation. MED, just distillation. There's no membrane, but in this case, we can utilize the membrane. Thermally driven. Just before the 3 processes, RO, FO, PRO, osmotically driven. But here, thermally driven. So, hot feed, cold feed, if you put this 2 condition here, this is a hydrophobic porous membrane. But just before the 3 osmotic pressure, hydrophilic non-porous membrane. So the hydrophobic porous membrane means hot feed to cold feed, temperature difference, only delta T. Temperature difference can make the water liquid to water vapor. Delta T is greater than 30. And delta T greater than 30, then vapor can move here through the pore. So let's say the room temperature is 20. Let's say room temperature 20. And your shower hot water is a 45 or 50 hot water. So you can feel that, wow, it's hot. That feeling is 45 to 50 degree. But delta T can be 30 degree, right? 20 to 40, 50, right? 30 degree. Then this is your shower hot water. This is your just cooling water. Then water can penetrate from here to there. Only here, vapor pressure difference, water vapor molecule. Water vapor molecule. You know that water liquid and water vapor, right? Water liquid is liquid, like this. Vapor is what? This one. Huh? Vapor is this one. You can see this is one. This is vapor. So you, and also why you can feel hot here? Because of water vapor. Water vapor is, you can feel hot, right? Water vapor is moving out, right? So delta T greater than 30, then this water vapor generated. Does not have to be 100%. Does not have to be 100 Celsius. This is a very funny science. When is the temperature for boiling the water? Who said that? That's the wrong science. Book. You need a condition. 1 bar, 25 Celsius room temperature. Then water is supposed to be boiled 100 Celsius, right? Without that condition, water sometimes can be boiled around 90 Celsius. Sometimes it can be boiled around 100.5 Celsius. Who said that? 100. It's a funny science, right? So exactly same thing you have to learn here. Membrane distillation using that scientific phenomena, vapor pressure can be generated anytime. When delta T has greater than 30s or 25, it's okay. Depends on the condition. 25 or 30, 20 sometimes, then water vapor generated. So you just only think that when you do that boiling the ramen or any kind of the soup, you imagine that 100 Celsius can make the water vapor, right? No, it's not. Water vapor can be generated anytime delta T is greater than 30 or 25. Difference, temperature difference, temperature difference. So this hot feed, cold feed, if we have this temperature difference around 25 or 30s, then water vapor is moving through this pore, this hole. That's the mechanism of membrane distillation. So membrane distillation needs a hot feed and cold feed, and the water is moving. When we apply this one, we have a really hypersaline system. For example, mining area, we have a high salinity process. For example, shale gas area, because we crack down that shale layer underground, and then it contains all that groundwater shale layers some dirty chemicals has a high saline water. Then we can apply this membrane distillation. So 100% theoretically rejection, it has low operating condition when we can use the solar energy, because this hot feed need energy, right? But if we can apply that hot feed using solar energy or waste heat, where is the waste heat? Where is the waste heat? Generation plants. Generator has a waste heat. Usually 60 Celsius. That's the reason we need a cooling water. Cooling water, if you put that cooling water into generation plants, electricity generation plants, it cool down, and then that cooling water get the temperature up to 60 Celsius. 60 Celsius. So cooling water, that is waste heat. It can be utilized for this one here, hot feed, cooling water. So cooling water around a nuclear power plant, around some power plant, the cooling water can be utilized. Okay, that is membrane distillation process. So most of the model we can explain after visiting my site and after lunch. We will start around 1:30. Okay, we will move to there now. So you can study for yourself. It's very easy mathematics here, right? Let's move there. My left. 움직입시다.
이거 끝.
아, 그거 끝이에요.
How's your lunch?
Yeah, good. Nice food.
But
Every day is a
you're a liar. It's just student union lunch, right? That's just for the student. Oh yeah, you're a student. Then it's delicious, right? So actually, to check up all the processes in reverse osmosis, forward osmosis, and membrane distillation, we have to check up overall balance, mass balance, energy balance, momentum balance, component balance, and also pressure drop, flux equation, and ICP. Have you ever heard of that, about this ICP? Yeah? Internal concentration polarization. ECP is external concentration polarization. But I don't want you to remember this. It's tough. And I will explain a little bit about that. So these are the modeling steps for all phenomena inside of membrane. This is a general description of membrane and transport model. And when we have this is a membrane, active membrane here. Let's say this is a feed in, feed out. But when we have this concentration in the bulk side, bulk, this bulk concentration can be same as this inside of membrane. Question. This bulk concentration, theoretically this concentration should be same as this one, right? But there's some divide here. Divide here. Why is that? Obviously this is a disconnected, right? when you see the Dr. Amir's animation, he generate this molecular dynamics with continuity of this two. There's no barrier here. So he consider everything as continuous system. You saw that molecular level. But most of the membrane, you cannot detect of inside of membrane. You can detect here, right? Put sensor in Burke side here also. Put sensor Burke side here. The feed side, permeate side, we can monitor the CF and CP. Feed concentration, permeate concentration. But inside the membrane, how to calculate, how to measure it? Dr. Amir only do that the simulation, right? We don't know. Anybody can develop that monitor to sensor inside a membrane? It's very thin. Yeah, it's molecular dynamics. You saw that the thinner layer is 10 angstrom size of that. That's the reason we need a modeling, because we don't know inside. But Burke and inside the membrane, they have some this divide. So why we have this divide? So my question is, diffusion is mass transfer. Same? Raise your hand. Same. Diffusion is mass transfer. Same. Raise your hand. Diffusion is mass transfer. Same? No? No. Raise your hand. Only one. Two. What's the difference? Tell me.
Diffusion transfer by molecular particles. This is depends on density of the two side, between the two sides. Transfer, there is no, we can transfer one place to another place without this place that all are same, not variation about the two, between the two places.
Similar. We will learn diffusivity, mass transfer coefficient, and partition coefficient. If you remember these three language in membrane, but then that might be enough for public officer. If you want to learn more, then study under me. Yeah, and I will give you a PhD degree. Simply, I can say that here this is diffusion. Then this minus this is mass transfer. Burke side monitoring result, mass transfer. But inside membrane transport phenomena is diffusion. So for example, we have a fixed law. We have a fixed law, this one. JA is mass flux, so equal to DAB, DC, dy. This is a fixed law, so this high concentration is supposed to move to low concentration, right? That is fixed law here. But sometimes this flux can be calculated A delta C. this is something like that. CFCP, right? Something like that, delta C. Feed minus permeate concentration. Something like that. Here's A or B, right? But are they same? What is this?
Concentration and permeate concentration. That's
Measurable, 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 right? A is a sum coefficient. No, coefficient, just coefficient. Then we can utilize what? Monitoring data, right? Right? CF, CP, right? But this is not actually saying this is we call the similar to. But this is a theoretically right expression. Depending on the distance, change of concentration. And this is diffusion coefficient, diffusivity. We call this is mass transfer coefficient. In this case, we consider what? Distance. In this case, we don't consider distance. But this is a measurable quantity. This is a measurable quantity? No. Inside here. So diffusion, it's a theory. Diffusivity is this one. This. DAB. Mass transfer happens measurable quantity. This is disconnectivity. Diffusion is continuity. Totally different situation. Diffusion has continuity. But mass transfer has disconnectivity here. Okay? So that's the reason we can utilize CFCP. Which one is simpler? Mass transfer is simpler. Why? Measurable. This one, simulation. You saw that. Dr. Amir was working there. But which one is more accurate? Huh? We don't know. We don't know. We don't know. How can you know that? How can you say with simulation, diffusion, even though I'm working on there, but how can you say that? Diffusion simulation is more accurate. We cannot say. This is measurable. Which one is more visible, tangible? Mass transfer. That's the reason engineers are using mass transfer. They don't want to use, that imagination. This is imagination. That's the reason. So I told you that. Statistics is grammar of science. Modeling is grammar of engineering. That's the reason. Modeling, sometimes we are doing simplification like this. We don't have to find diffusion coefficient. What we have to do is measure. Flux, water flux can be measurable. So it's volume change within the specific area, flux. Measure. What is this then? Just coefficient. We can do curve fitting. If you do the curve fitting, then A can be calculated simply. That's engineering. That's engineering. 여기 선풍기 좀 틀어주세요. Okay. So I will explain that this active membrane, this is active membrane, but here this is active membrane. Here. See? And this is a support layer. 아니요, 거기 다 돌아다니게. This is a support layer. You have learned that. Skin layer, support layer, right? Support layer is a different material. Skin layer is a polyamide usually. The other one is a polysulfone and sulfonide, something that is support layer. Support layer is related to some ultrafiltration or microfiltration performance it has here. Whatever that is, this is a we call layer. This is a skin layer. I'm sorry. This is a skin layer. This is support layer. Okay, skin layer and support layer. When we have a same language, what's this meaning? Symmetric. What's the meaning of this? What's the meaning of this? Symmetric. Symmetric means opposite is asymmetric. Right? When we have a skin layer only, then if this is enter, feed, then permeate is permeate. Then this relationship looks like this. But if we have a feed here, then permeate is here. Right? Feed 2, permeate 2. Then similar trend. In this case, we call that symmetric membrane. Symmetric membrane. But what happened here? Skin layer here. Skin layer here. Then symmetric. Like this, skin layer here. Then if you go there and drop and a little bit drop, something like that. Right? Right? If you go here in this way, but drop, drop, something like that. We call that asymmetric membrane. This is the flow direction depends on this skin layer, support layer. This is a symmetric membrane. Membrane is here. Skin layer. But if you change it, that flow direction from here to there, a totally different phenomena happens, right? Active layer, actually it is supposed to reduce 99% of salt, right? But porous media, after that, just flow channel, this is. But once you change the direction, cannot be same as this one. So, active layer makes the membrane asymmetric. This asymmetricity makes that this different phenomena of the fluid. We call that A is bulk region, H is bulk region also. See there, H, A here is a bulk region. That means there's no effect on membrane, just flow area, bulk. Boundary layer region 1, B, boundary layer region 2, G. They are similar here. Surface region 1, skin layer region, porous support region, surface region 2. So let me move on to there. Bulk region here, no concentration gradient. What's the gradient?
The difference.
You know, art and science are similar. It's artistic language, right? It's art language. This is gradation, right? Dark to lights, right? Dark to lights, dark to lights, right? 됐어요. 그냥 제 거 써요 지금. Gradation. What's the gradient then? Huh? Gradation. You know gradation, right? It's art language. Change that color from dark to lights. That's gradation. What's diffusion? What's gradient? 됐어, 했어. 됐어. 이 커피 좀 갖다 주세요. 예, 아이스 커피 좀 주세요. Is it different? Gradient needs. This is gradient. This is mathematics. What is the meaning of this? Delta. What's the meaning of that? Change. Change of concentration with respect to change of distance. Okay, that's gradient. This is definition. Gradient definition. Change of something, we call that concentration gradient. Then change of concentration with respect to change of distance. What about temperature gradient? Change of temperature with respect to temperature, change of distance, right? That's gradient. What's gradation then? Change of color with respect to distance. Same language. Same language. So art and science has like a coin. Face is a science, tail is art. It's like a coin. The two sides of coin, face and tail. Gradient is this one. Gradation is that one. Same idea. Same idea. So if you want to study more under me, I teach you in this way. Yeah, thank you. Very interesting, right? So I link my artistic insight into the mathematics. Don't forget that gradient in science and engineering. Same idea, gradation. Gradation. Then, let me move on to the next slide here. No concentration gradient. What's the meaning of that? No change to distance. That's right. That's Berkeley region. Okay, you guys are very good students, right? Or am I a good teacher? Right? Second one, concentration change, right? Concentration is changing. Then there is a gradient, right? Here there's no gradient, right? Here there's a gradient here. So when that seawater squeeze to this membrane with high pressure, so in common sense, concentration is increasing. It's a common sense. So this increased concentration is supposed to move through there. So within this region, concentration is squeezed and polarization, we call that. concentration polarization. Polarization means is a squeezed polarization, concentration polarization. And then here, this region, membrane, this region, diffusion happen. Something like that. Something like that. What is this? Okay, good student. Gradient, gradient. This is gradient. Change of concentration with respect to change of distance. Gradient. Here, diffusion coefficient, diffusivity. We call it diffusivity. So within here, diffusion start. And then here, salt rejected based on this here and there. This is a rejecting concentration of this. Skin layer is active layer here. And then support layer, most of that. Let's say I gave you this coffee, right? Where's my money then? When we start this coffee with water, this is pure water, this is coffee. When you start, just put this on and wait here, just wait here, diffusion happen, right? But if I stir this using this, then mixing, we call it convection. Convection happen. Is it that winds, fan, convection or diffusion? It's convection. Just a forced convection. Forced. Artificial convection, that one. Without that winds, fan winds, some temperature or air is moving. That is? No, that's natural convection. That's natural convection. That one is a forced convection. Different. Whatever that is, something is moving here, that is convection with velocity. With velocity, then velocity related to, do we have a velocity here? There's no velocity, right? There's no velocity. Only concentration change with respect to distance. Only that one. When some phenomena happens in distance and gradient, then diffusion. But something move with velocity. Something move with velocity, then we call it convection. Convection. So we have natural convection and forced convection here. Okay, then support layer, most of the convection happen, not diffusion. That's the reason here, very flat. Very flat here. After that, there's another disconnectivity here. This is a skin layer, this is a support layer disconnection here. Then concentration is supposed to a little bit high. Then this is another desorption part of this membrane. And this is similar to B here, a little bit here. Not, even though not squeezed, close the membrane, there's some concentration increase. Close the surface, some concentration increased. Similar to no concentration gradient. This is the membrane phenomena. You can graduate today. Yeah, that's it. That's it. Simple, right? But there's a lot of models, solution diffusion model, irreversible thermodynamic model, pore-based model, and here, diffusion-based model, pore-based model, Kadam-Kachowski, Spicoli-Kadam, surface force flow. You want to learn? Then you have to enter this school first. Okay, but you can study. If you have a question, then send me an email or send your staff or student to me, or you can visit me. Okay. As you know well, that this school is very famous in water. Number 1 in Korea, and number 7 in the world. Number 3 in Asia. So this is a fixed law. States the diffusion of component A. This is viscosity. This is Newton's law. This is thermal conductivity Fourier's law. So these three, mass, momentum, energy transfers, are same phenomena we call transport phenomena. I will skip that. If somebody asks to you, then give this note to them. Study it. There's answer. What I can say here, this is the procedure why concentration switch to. Actually, this is a concentration play, right? High concentration, low concentration, but it abruptly switched to pressure here. Here, right? This is a flux, water flux. Applied pressure, osmotic pressure, this minus this. Why? But we were talking about concentration, but it was switched to the temperature, the applied pressure and osmotic pressure. This is the procedure how to switch using thermodynamic, Henry's law, chemical potential fixed law, water flux, math balance. That's it. So these are the thermodynamic parameter. Theoretically, should we measure? Or these two parameters are measured. Applied pressure I give, right? 60 bar. Osmotic pressure we can find. Seawater is around 30 bar, 25 to 30 bar. This is measurable. Flux, water increase, flux. This can be compared with these two. A is just fitting coefficient, right? We call this water permeability coefficient. B is solute permeability coefficient. So membrane company only offer this A and B parameter. They don't want to release any kind of this diffusion coefficient, this some fraction coefficient. They don't want to release here. They just release A. Right? That's reasonable, right? You don't have to increase the uncertainty. Just make it simple, A. Make it simple, B. So they release A parameter and B parameter for membrane performance. There is some membrane number here. If we have a more membrane number, finding that company and click this membrane number, then you can see that A parameter and B parameter. So A and B shows that when A is high, that what's the meaning of that? Water permeability is high. High flux. When B is high, then when B is small, then high rejection. High rejection. B is small, then high rejection. Right? And A is high, then high flux. High rejection, high flux can be happen together. High rejection, high flux can be happen together. It's controversy. If you have high rejection, then low flux, right? If you have high flux, then low rejection, right? So that cannot be go together. They need some optimal point. Some high flux It depends on the needs, customers' needs. We need a flux, high flux, then we compensate for this low rejection. Something like that. I will skip this. Polarization phenomena, I told you that diffusion used to meet this membrane, then membrane, around the membrane, the concentration is going high. Skip it. If somebody want to learn this, then let them know, study it inside. Fouling, membrane fouling is very important. What's fouling? You have learned, right? You have learned fouling, right? Professor Kim, how many lecturers so far? Kim,
3, this is the 4.
3? Did me is a fourth. I'm fourth. Okay. Then most of the people say about this, right? Fouling. This is organic fouling. The scaling related to salt, Ca2 plus, Na plus, or something like that. Biofouling is bacteria or EPS. Colloidal fouling is colloids. We can segregate that. There's 4 different fouling: organic fouling, inorganic fouling, biofouling, colloidal fouling. It has responsible constituent NOM2, metal oxide, and other bacterial microorganism. Fouling mechanism is a pore narrowing, pore plugging, pore gel formation we have. Cleaning method, we need some chemical cleaning, physical cleaning, something like that. But in the modeling, still we have a question about scale formation, cake formation, biofilm formation. As a modeler, we developed this model. But do you think it's reasonable? Scale formation, can you define it? Cake formation, can you define it? Biofilm formation, can you define it? Attachment, growth, detachment. This is common sense. This is common sense. Depends on how to define it. Modelers work. So I developed that model. Who decided this model? Me. That means, can you trust me? You told me that looked like a model. I'm modeler. Can you trust me? Yes. Yes, right. Then we can utilize it. If you cannot trust me, don't use it. Just measure it. That's faster. So for the scaling thickness, there is some power here, R, gamma, and some cake layer thickness, delta, depends on some velocity. Biofilm formation, growth rate. We don't know growth rate. How many microorganisms in water? Thousands of thousands, something like that. We don't know. How to calculate this growth rate of microorganism? If you believe me, use it. But this is just a rough application because the fouling is still unsolvable. Fouling is related to first, we don't know, some pollutant inside the water. We don't know how many metal oxide inside the water. We don't know. How many bacteria organism in the water? We don't know. That's the reason fouling is a still unsolvable approach. But I can apply that there's some resistance like a pore blocking resistance, cake resistance, concentration polarization resistance, membrane resistance. If I can make it, then total resistance from fouling can be added up. And then each one can be calculated in this way, but that is only followed by that theory. So another internal fouling is a physical compaction. So if we have a high, this is cross flow. Now you can understand, right? Cross flow, right? Cross flow, then high pressure cross flow make this membrane thinner. Compaction. This compaction make that inside some space inside the membrane is compacted. Then water cannot be flow well. Cannot flow well. The compaction of membrane and chemical degradation sometimes take formation of reverse osmosis. So I will skip it. Thank you. You can graduate. I will give you examples. Application, first one is molecular level. So we don't know new membrane, how much foulant inside, how to membrane happens, how to clean the membrane, we don't know. So we can consider scale simulation, this scale in simulation, 1 angstrom. You saw that, right? The molecular dynamics. We call that MDS, molecular dynamics simulation. You saw this one. 1 nanometer, this reverse osmosis, micrometer. This different size can be modeled. First one is molecular scale, molecular dynamics. We use the Schrödinger equation. If you want to learn Schrödinger equation, so I can toss that the chemistry, physical chemistry, and organic chemistry, and Einstein's relativity theory. And all together is a Schrödinger equation. If you want to learn, tell me. Tell me. So it will take half a year to make understood. Okay, Schrödinger equation was applied. Charge, van der Waals site, molecular level, dihedral angles, bonds. Okay, I will skip it. Quantum mechanism, Schrödinger equation, molecular mechanism, what Dr. Amiris was doing, molecular dynamics. It's related to the computational technique and the movement of the atoms, and also evolution of system as a function of time, temperature, and pressure. Then it can be applicable. The potential energy, again, what is potential? Potential is energy. Is potential energy? Potential energy is just potential, not energy. And if we have action, then that's energy, right? So potential energy added up, they are bonding energy, angle. It has a chemical structure as an angle, right? Angle and dihedral. Dihedral means something like a dihedral. Van der Waals, Coulomb energy, external force. That all internal energy is added up. Sum of that, bonding energy, angle energy, dihedral energy. And strong point and limitation, molecular dynamics deal with the bigger system and can simulate the dynamic process, diffusion phase transition. Limitations, the force fields are valid for that limited type of material. So material information is the critical. The material is important. There's no bonding, breaking, performing involved, and size of system is a 10 to the 4 atoms or few nanoseconds. You know, interestingly, Dr. Amir, I don't know he mentioned or not, to see 1 nanoseconds phenomena, how long computer should run? Give me the number. To see 1 nanosecond molecular dynamic phenomena. How long the computer simulation must run? 1 nanosecond to see 1 nanosecond. You saw that that movement that is maybe 0.2 nanoseconds. To see that 0.2 nanoseconds, water is moving to inside the membrane like this, right? Water is penetrating into the membrane. First, to generate all that system, that phenomena happens 0.2 nanoseconds. We have to run the computer 2 weeks to generate the shot. That's a 20 seconds animation. 20 seconds animation implies 0.2 nanoseconds. 0.2 nanoseconds. We cannot see because we are living in that hour-based life, right? Because my lecture is longer than 1 hour, but you can get bored, right? Let's say that with hour-based life, that is, record that. Hour-based life, want to see that nanoseconds phenomena. It's ridiculous. It's ridiculous. But to see the 2.2 nanosecond words, now the computer technology should run for 2 weeks. It's very interesting. That's the limitation. But as time goes by, that quantum computer is developing now. It's faster than now. So I'll skip that. This is some procedures, initialization, equilibration, and the production system. Carbon nanotube inside here, and he generate this one. This is a carbon nanotube here. This was generated 2 years ago, but it's too old. But this carbon nanotube start this. At some point start to penetrate, let water penetrate into this other side. And he's working on ammonium functionalized graphene, then a functionalized group can be linked graphene side. And also MOF, metal organic framework, metal plus organic linker can be simulated in this way. I will skip it. The micro size of the computational fluid dynamics is, that is, you saw that Seung-ji, who showed you the reverse osmosis system today, that he is working on this. Computer technique plus fluid dynamics, this can be visualized in this way. So flow, it's exactly same phenomena can be applied for the membrane side here. This is a tank mesh design. Inside the flow can be visualized. And this is a typhoon, also flow. And here, this is the spacer. You saw that here, the spacer. Spacer look like this. What happened around the spacer? I told you that. What's the role of spacer? Reduce down, concentration polarization. Then down. Then we can make water penetrate into here because all the concentration was reduced down here. CP was reduced down around here. So this can go to that way, penetration. And this is another reverse osmosis. And if you change the current, not like a cross current, co-current, counter current. Counter means this one. Co-current means this one, same way. In forward osmosis, so did you see the small one is a forward osmosis system? You didn't see that? We had, but that was in the lab. The forward osmosis can be tested also using this soft module, simulated. Forward osmosis has this type of membrane and spiral wounded. And then that initially it shows a high performance, but as the distance go longer, then the performance is reduced. This is DCMD, membrane distillation in this case. Which type of location of spacer can make better performance of water permeation? Can you see here? And some different color here. That is temperature difference. So this is a hot side, this is a cool side. Membrane. Okay. And macro modeling is process modeling. So you saw that the small size of this reverse osmosis, and it can be designed in here. That is feed temperature, feed pressure. So we can adjust the feed temperature. We can adjust the feed pressure for the same membrane system you saw, right? And how to change that feed temperature? You saw that tanks. There is some water bath. The water bath can be heated. Then we can adjust the feed temperature. Feed pressure, that means we have a pump. Pump application, we can adjust that one. So these cross dots are the measured value. You can see that very interesting. Membrane ABC, membrane ABC. This is a recovery flux. This is rejection. They are all different. But interestingly, they offers only one value of A and B. Very interesting, right? Very interesting. So I published that in a very good journal. So they offers only A and B value. Conclusion is stupid. Don't believe that. Contract is more important. Contract. 5 years guarantee or 3 years guarantee, something like that. Contract is more important. This is our student product. Okay, do you want me to explain it? This is overall balance, component balance. Want it? Do you want it? Okay, I skip it. So we tried that how to design this module of forward osmosis. This forward osmosis make co-current, countercurrent, big difference in the membrane positioning. And how much percent we can optimize that model. Then this DS means draw solution, FS means feed solution. And when we use this forward osmosis module like this, then some special design we have to consider. That is a point. PRO DCMD has a model. The interesting point is dynamic model. I apply that different concentration, feed concentration, different temperature, and we can adjust the 0 to 8 levels. Kalman filter approach, you can see that most of the measured data and simulation data and very high performance. So this is measured data, but if you desired temperature here, desired flow rate here, then we can cut, and also desired concentration here, then we can cut. Eventually, optimized control makes more flow rates, and optimized control makes a lower concentration. That means high rejection and high flux might be possible. So that's the concentration. The optimal control is important. Numerical optimization, I will skip it. It's not meaningful to you. Superstructure optimization means reverse osmosis system has some pump station. The pump station needs typical link to energy recovery system. So pressure vessel structure can be optimized, and then can be some control theory, and then how to make it arrangement for, this is a total cost model. Then considering all reverse osmosis system like this, it's a superstructure. Superstructure understanding, it will take almost 1 year. Yeah, so that's the reason I skip it. Thank you. Done. Yes, that's it.